So with that exciting introduction, let's see if this works. Sort of. Okay, so I'm going to show you some data from the HSE project. Yusra introduced it. Here's a picture of the camera when it was being assembled, just to give you an idea of the contrast. Those are 4 LSST rafts on the same scale. That is the same in microns. The pixel scale is actually slightly different. So the stuff we're getting from HSC is a big field. It's about half the size of DES, and it's obviously much smaller than LSST. And for some reason, I'm not getting my advancing properly. Interesting. Here's the LSST focal plane. You'll see one thing in common between this and the previous focal plane. And I am unhappy with the way this is working. There we go. Which is you can see the characteristic difference in the colors of the CCDs. That's due to the AR codes. And you'll see the same thing if you look closely at this focal plane. So LSST is also going to does have CCDs, 2 different types, ITL and E2V in the focal plane, with slightly different properties. Okay, so this is some real data from a real LSST CCD on the sky. This is raw, though I've masked out some glowing columns and things like that. This is actually from the auxiliary telescope. I'll come back to that towards the end of the talk. This is obviously M104. You don't want to know why it's sideways. You'll see a lot of bias structure there. And in fact, those are the boundaries between the amplifiers. We're using CCDs with 16 amplifiers. If we go back, you'll see you can see substructure in the bias frames. That's a little unusual these days, but they subtract out very nicely. So we're beginning to get some real experience with the LSST devices, though we're expecting a lot more. So what's the ISR? Here's a simplified version of the ISR. I think I've caught most of the effects that keep me up at night in here. It's complicated. And all of these terms matter. Exactly how nonlinearity works, how the crosstalk works, how the CTE works is something that will definitely show up in the data. I'm not going to go through this set of equations, backing them out one by one. That would be boring. I don't have time. But you can't forget about anything in here. And for different cameras, different things matter. Fortunately, most of these corrections that we're going to make are totally standard. There's nothing new or interesting or original about the LSST in this context. Some of them are a little tricky. For example, there's a lot more bias structure than you normally see in cameras, though of course you do see it. Some of the amps are pretty noisy. We've got a very big camera, very big telescope, and quite long integrations. It's not a spectrograph. I don't think that's a problem, but it's more than you might expect. However, look on the plus side, this isn't DES. The tree rings are pretty weak. And in fact, the ragged gate, the variable pixel size is also pretty small. Brighter, fatter is roughly as expected. I'm not going to go on about things like brighter, fatter corrections. They're there. I think we're dealing with them as well as anybody else. I'm not claiming we've pushed the state of the art there. So the current correction techniques are not perfect. There's some serial CTE. Probably people on this phone call like Aaron Rubin know better than I do from traps in the serials. There are some parallel CTE features as well we're going to worry about. Charge transfer efficiency. From time to time, there's been some tearing or tarring. I've never known which it is. Problems with the CCDs, we're getting the holes out of the devices. That seems to be cured at the moment by exactly how we're running the voltages. I guess I'm mentioning this because there's always an interaction between the people who are writing the software and the people who are building the camera, and we do collaborate, and we're going to continue to find surprises. Crosstalk appears to be a function of signal level. I know this is something that Des saw as well. I think Des' crosstalk is probably more complicated than our crosstalk. We see very little outside this individual CCDs, cross-raft. I can't remember if it's measurable at the moment. Certainly nothing between the rafts. Our cabling is structured rather differently from DES. However, it does seem to be nonlinear beyond the nonlinearity corrections in the rest of the audio chain. We don't understand this yet, but we will obviously deal with it. The chips show thickness variations up to about 20 wavelengths. That's wavelengths in silica, and the refractive index of silicon is about 3.6. But there are some really quite significant wedges present in these devices. This is some data, I think, at 1 micron taken in parallel light. And I would remind you that the LSST beam is f1.2, it's an annular beam. So this isn't characteristic of the fringe patterns. But those of you who spend your lives looking at CCD fringing will recognize that this is qualitatively different. Instead of being a pattern that looks like contouring in the Lewisian gneiss of northwest Scotland, it looks like hillsides sloping away. The fringing corrections may be fun. Big thickness variations like this give more components of independent fringing. ZTF sees that, I think, due to their field flatness. Again, we know how to deal with it, but it's something that is not characteristically seen. The chips are only 100 microns thick. Only, of course, is a joke to those of you as old as me. But that's significantly thinner than either Hyper Supreme Cam using 200 micron Hamamatsu devices or DES using 250 micron LBL devices. So we're going to see back of the chip artifacts, what the scattering off the channel stops in bluer bands in either HSC or DES. We're going to see these horizontal structures coming off the bright stars. Okay, I distrust all A to D converters with good reason. Some of the effects I'm about to show you in HSC may or may not be due to our A to Ds. Almost all cameras, I think ESS may be the exception, show weirdness from the A to Ds. We're probably going to see something like this. I haven't seen it coming out of the lab data yet, but it's easier to see on Sky data perhaps than lab data. So we will see. And of course, there are lots of other things we're going to find out about this camera that we don't know about. So this list is because of this list, and because at least we're worrying about these things and working with the people who built the camera, was the basis of Yusra's claim that we expect to get the ISR under better control than you want to yourself. You do not want to understand the details of our signals chain, coupling down to the details of our A to Ds that mess up the signal. That is something you really, really want somebody else to do for you. I'm sure we'll miss some number of features that will show up in the science data. So I'm expecting feedback saying, but you didn't fix this, which is doubtless true. And then I think it's our job to fix it. Okay, so let's talk about an ideal universe. We're getting a bit too close to operations for LSST to protect for the Vera Rubin Observatory to pretend this is the case, but let's pretend we are in utopia. So all our extraterrestrial photons would be superimposed on a uniform background. So if we were looking at an empty part of the sky, which doesn't exist at these depths, it would just be uniform, except it wouldn't, because in the data, this is getting in towards the flat fielding questions, the larger pixels will be brighter than the small ones. Due to random variation in the mask set, not all the pixels are the same size in microns. Due to things like tree rings, which are doping structure in the chips, edges where the electric field leaks out of the chip, and that changes the effective pixel size. We have similar things down the median of the E2V devices. There's a bleed channel block, which I think throws away more pixels by always being there than occasionally dealing with bleed trails from stars. But it does affect a few pixels down the ridgeline where the pixels are not the same size. And then of course there are Jacobians. There are optical distortions, and if you're working in tangent planes or tangent plane distortions, which change a constant surface brightness, uniform background, into a function structure. And of course, more sensitive pixels will be brighter. So if there's a spatial variation in the real QE, or a spatial variation in the filters, band passes, or central wavelengths, that will also make pixels that are brighter or fainter. So the first effect is geometric on the device. The second effect is real genuine QE, changing the probability that a photon above the atmosphere, or just above the telescope in this case, will be absorbed. Okay. And of course, then also we have the problem that ghosts deliver extra light to some pixels. So great, that's why we flat field data. Because when you flat field data, it deals with all of these problems. You never need to worry about it ever again. So is that true? Well, just a sketch. So here is the pixel sensitivity. And I've drawn some nice, regularly well-behaved tree rings where I've assembled the jigsaw so that all the CCDs from pieces of silicon lie together in the focal plane. In reality, of course, the tree rings and things like that are dependent on the position, they're per CCD. Then QE variations, that are these blue dashed lines, which vary generically from one side of a CCD to another and from CCD to CCD. I'll show you some data that justifies this. Then the optics, this orange curve is the sensitivity. This is vignetting. This says the edge of the field, the telescope delivers fewer pixels. So you have to worry about taking those terms out. And in fact, I think I drew this figure wrong. I shouldn't have bothered with the purple line, the magenta line. Okay, so that's what the sensitivity looks like. But I also talked about a uniform flat field source. We don't have a uniform source. So dome illumination typically looks something like this, where you have a non-unit, you would like everything to be uniform, that's in blue. In fact, the lamps don't fully illuminate the screen uniformly, and if you have any vignetting, that couples back down to the illumination seen at the camera. And also there's ghosting, and I've drawn a reasonably characteristic form of ghosts, and maybe I haven't, but I've roughly drawn the amplitude correctly. So if you take a flat field and interpret this green line as being flat, you'll get the sensitivity wrong, because it's not it's an additive term, not a multiplicative term. I've multiplied the green line with the sensitivity curve from the previous page, and you get a black line. So that's what a dome flat looks like generically. Here's the sky illumination. Well, it's just a little bit different. The ghosting is a little bit different because the spectrum of the light is a little bit different. The CCDs have slightly different performance because they're also chromatic. And I think this is part of the answer to the question that was asked Yusra about what does the moon do to, I'm going to come back to that in a moment. So here we have a sky flat, except we don't. Here's another sky flat. Here's a sky flat taken through the same filter on a different night when the conditions are a bit different. So in the red bands, for example, the OH is different. So the color of the sky is different. In the blue bands, the moon is different. So the color of the moon is different. The ghosting depends on the moon. So you don't just have one sky flat, you have multiple sky flats. And I'm not here talking about twilight flats, which have all their own problems with gradients and polarization and things like that, and are very blue. I'm talking about sky flats taken by medianing up a lot of data. If you take up enough data, by definition, I guess it's uniform, but it doesn't represent the conditions on a given night. So here are flat fields. Here are four examples if I count. A dome flat, two different sky flats, and the number that I actually want. I think I actually want the one with the vignetting taken out. But this blue curve is the product of the CCD quantum efficiency and the system quantum efficiency. So this has structure in it, which is different from either the dome flat or the night sky flat. Okay, just to remind those of you who haven't seen these before, this is a genuine, in fact, a star flat, but this tells you the difference between one of these gray lines and this blue line, which you can measure using stars. I'll come back to that in a moment. And they do indeed have these characteristic structures due to ghosts in the camera. Okay, so let's just have a look at some hypersupreme cam data. And you can't see all the individual CCDs because of the way I made the figure. Sorry about that. Here is one CCD, so that's 2K by 4K. So you should think about this as being one LSST device. It's actually a little bit smaller because these are 0.168 arcsecond pixels on axis, and LSST is 0.20 on axis, but that's kind of irrelevant. This is a glowing amplifier that we've masked out. So you see structures, and you say, well, that's because you're using dome flats. Well, maybe that's what you say. This is early data taken a long time ago. This is the previous exposure taken at 30-second exposure time. So you see things have changed, and you might think this is nonlinearity. And for a while we thought it was, and for a while we thought it wasn't. And I'm not sure what we think at the moment. But dome flat, the structure of flats does change due to nonlinearity, but also due to A to D effects, which is the other possibility. So dome flats are not ideal. Neither are sky flats. So here is a G-band flat, dome flat from hypersupreme cam. And what I've done here is I've fiddled and I've manually corrected the overscan, of course. I've multiplied the chips by my estimate of the gain. I've corrected for a rough QE term. I've corrected with the vignetting, and I've corrected with the Jacobian, the spreading out of the non-uniform surface brightness in pixel coordinates of a flat field screen. So that's the dome, and I've helpfully color-coded with part of this slide you should be looking at. and there's a sky flat. And if I zip between them, you'll see the structure is qualitatively different. In fact, rather amazingly, you'll see that the QE is different on the side of the CCD towards the serial register. That's a feature of these chips. We used to have things like this in some of the E2V devices. I think it's not serious at the moment. But in general, CCDs don't even have a uniform quantum efficiency within themselves, let alone CCD to CCD, a term I've taken. Here's another band. This is now the I band. This is a dome flat, and the previous one was a G flat. Yeah, this is the dome flat. It's brighter around the edge. That's a little bit surprising. I believe I got the Jacobian right. That's the dome flat, and that's the sky flat. What's going on here? Well, the main effect here is that the filters are not totally uniform. The filters are a little bit more sensitive towards the edge of the chip, so that brings up the dome. But that's different in the sky and the dome flats because the SED is different. And the other term is these things, these rings that you can see. Those turn out to be because at those radii, the filter couples more efficiently to the night sky lines at other radii. So its central wavelength changes as well as its bandwidth. So the night sky lines, as they come up and down, change the appearance of the background sky. So this is supposed to convince you that just as there is no good dome flat, there is no good sky flat. Now, it's worse than this, because some of these effects change things. Well, this is the effect I've just shown. So some of these effects that you see to do with chromaticity work differently in sky and in flat fields. Now, some of what I showed you is due to the HSC flat field system. We fixed that mostly, and the filters. Those rings in the I band are definitely filter effects. We do not expect that to be present in the LSST, but we haven't got LSST data yet. I believe it is LSST because that's the part paid for by DOE, which is still called LSST. So I can't have my wrist slapped for that. Okay, but some of this really is due to the different SEDs, the photons that are coming in. And there's also the fundamental choice to be correct for the flux of an object or for the surface brightness. And for doing different things, you want to do different things. If you're trying to do stellar photometry, you want to correct for the flux. If you're trying to remove the surface brightness or study the infrared cirrus, remove the sky background or study the infrared cirrus, you're probably actually more interested in surface brightness. Okay, that's what it says there. Okay, so just to remind you, and I tipped my cards on this, the normal way you estimate the sensitivity of a resolved source is to use star flats, or equivalently large areas of imaging with suitable dithering. Those should give the same results. We're clearly going to do both in the LSST. We'll take star flats, but we should be able to demonstrate those are equivalent to the ensemble of all the data we take under all different conditions. And that basically says that we replace this blue line, which I want to know, with this set of stars, all of whose brightness I know. Now, of course, I don't really know their brightness, but by dithering stars around the focal plane, I can solve for both the spatial variation and the temporal variation of the, solve for the star brightnesses and the temporal variation of these blue spots. So it's possible to construct a set of blue stars that tell you the true sensitivity to stars. Okay, so we'll certainly do this. In fact, the talk that Eli Lycroft is going to give tomorrow will show some of these results. We'll probably be showing some of these results for the hypersupreme count, though he didn't analyze the data sequences that we took. In fact, luckily, or maybe unluckily, because we'll be able to prove ourselves wrong, LSST has additional hardware. We need to know the color of the sky. To remove the sky, you need to know the color of the sky so you can flat field it correctly. As I said, I think that's probably part of the problem Des is seeing. I showed you problems that was coming up in HSC, where we see very different things in the sky flats and the dome flats. I didn't demonstrate, but those actually vary with time depending on the emission of the atmosphere. The optic spectral characteristics. We need to know the filter pass bands. We need to know them incredibly well. According to the supernova folk, we need to know the pass bands to 1/10 of a nanometer. We need to know the detect QE curves. We need to know the filter pass bands, which of course are multiplied by the optics and the detectors in practice. We don't know the filters aren't going to evolve. This is probably a matter of making sure to have enough cavalry to win the charge, whatever it was at Waterloo. But in Sloan, at least, the filters evolved with time. Now, we believe that particular problem has been solved. We know what caused hygroscopic behavior, but we don't know for sure what's going to happen over 10 years. We have to be sure that we would at least be able to catch a global shift. Okay, some of my more enthusiastic friends would also like to measure the absolute throughput of the system so that we know the flux in nanojanskis. We're not paying for that. They can do it if they like, it'd be fun, but we're not going to do that. So we're initially going to tie our 0 points to CalSpec standards, which some people would tell you were the same as measuring things in Janskis. Maybe they are, maybe they're not. But it probably will get us down to something like 1%, maybe 1.5%, depending on who you argue with. So think of the fluxes being in Janskis, although the tie down is not at the 10 to the -3 level, 10 to the -4 level, as can be achieved by NIST photodiodes. And it's certainly easy in platinum furnaces hung off trees at Palomar, but that is no longer the international standard. So though it would be fun, I don't get to do that at Sarapachan. Okay, so what does the hardware look like? We have a flat field screen. This will not surprise you. Here's a picture of the flat field screen. Just to give you an idea, it's quite big. This is a big telescope. It's only a 6.5 meter in some sense, but it's also an 2.2 meter. So here's the flat field screen assembled in Tucson, which is illuminated by shining light off this widget. This will obviously be painted white with a well-controlled BDRF, bidirectional reflection. Okay, we also have a tunable class 4 laser. A tunable class 4 laser is a sort of thing where you get unannounced inspections from the health and safety people, at least we did before COVID-19, who want you to show you your licenses. These things are extremely powerful, but you need a lot of power to be able to put light all over that and illuminate the focal plane. So this means we'll be able to measure a set of monochromatic dome flats. This is similar to the system using using LEDs on DECAM, but with rather more control. And of course, we're using photodiodes and spectrographs to monitor the behavior of this system. So we know how bright the flat field screens are, and we know what the wavelength of them is. And that's one of these typical blue-green splits. It's awfully pretty. Okay. We'll also be able to separate the ghosties and the ghoulies using the collimated beam projector. This is a thing called the CBP. And just because some of you may not know the distinction which I make, but I think we should all be making, the ghosts are the things in your optical system which are deterministic. You can calculate those by propagating light through your system, reflecting 50% off the edge of the filter transitions at those wavelengths, 10% back off the CCD, and then that rattles around inside the optical system. And eventually we end up with beautiful things that look like this. This one's hypersupreme cam. And then the ghoulies, which we're also going to have, but I don't know how bad they're going to be yet, are the light that comes in by light paths you really didn't want, but they happen anyway. Scattering off the baffles. This one, I think, comes off the inside of the L1 lens, the front lens on hypersupreme cam. Scattering off the shutter blades as they transition over the system, those sort of things. We're going to see those as well. And they all give you light in the focal plane. So we also have a little widget called the CBP, which stands for the collimated beam projector. And what this is basically is a very small telescope, a 20-30 centimeter telescope stuck up here, which is able to project light down through the LSST optical system, M1, M2, M3, then through the camera, and form basically diffraction limited images on the camera. So we can project spots. That's what it looks like, sitting in the basement in Tucson. It's still sitting in the basement in Tucson as far as I know. Observe the G clamps. I believe those are due to seismic isolation on the mountain, but Patrick Ingram, who had this thing built, can confirm that. This is the prototype that we took down to DES. This is in the Blanco. This was no longer balanced on the table. It was balanced on the first time I saw it. This is Michael Hotlin, who is off doing things on LIGO. But basically, it's a Takahashi 18 centimeter astrograph. We send light down from the integrating sphere and bounce it out. And if we do that, we can form a spot, in this case on DECAM. the optics weren't terribly good. We didn't form very beautiful spots. But the interesting thing about this is that when we form a spot here, the only light that goes into this spot is the direct light, and all the ghost light gets scattered around everywhere else. So this is essentially a synthetic star flat, except we're driving it off, in fact, the same laser as we drive the flat fields off. So we can put down a set of monochromatic point sources all over the focal plane, but also separate the ghosts and the ghouls, because that is the pupil of the CBP, just one of the ghosts that we're getting in there. Whereas that is the pupil of the entire 4 meter. So by using the CBP, we can very cleanly separate these ghosts, which are real ghosts because you could calculate them, from the direct light in a way that's very much simpler to do than with stars, where you get all of them spread out over this size. And we have no idea what this thing is. It's called a dandelion. We hope it's a feature of the way we did this down in on the Blanco. We hope it's a Tololo feature, not a Pachon feature. But we don't know that yet. But it is definitely called dandelion. Okay, so having done that, we can do the standard thing. Now we're using CBP spots, which are now polychromatic, as opposed to star spots. And we can do a bunch of things. One is we can reconstruct the scattered light, and I've drawn this here. You'll see there are quite big residuals due to the jumps, and I've only used 5 spots or 7 spots or something per CCD. This is just a sketch. But we can also scan in wavelength. So I can tell you what this ghost looks like as a function of wavelength. I can tell you what the sensitivity really looks like as a function of wavelength. Yeah, you can recover it pretty well. So we expect to be able to do this. Now, with all this information, I can synthesize a flat field for any SED, whether it's a white light SED or the light of the moon, sounds like a song, or the light of the IOH mission, or of the stars I'm interested in, galaxies I'm interested in, for any SED. And I can either recover the object flux of the surface brightness. There may be some large scale corrections due to the illumination of the flat field screens not being quite the same as that as flat as the sky. There's no reason why we can't take out the very largest spatial modes on sort of 3-degree scales using on-sky data for the uniform surface brightness sources. That seems likely, but the ghost ghoul direct light split can be done properly, I think, using dome flats, which have the advantage of being stable. So once you've done your star flat analysis against the dome flats, and the dome flats don't change, just the system changes, you can track what's going on. Okay, so the current plan is to flat field the sky's surface brightness using its known SED on any particular night, any particular exposure. I think we can measure that using the next piece of kit that I'm going to talk about in a second. You can certainly do it using narrow and using broad bands, but then you have the problem of calibrating all your multiple broadband filters simultaneously as they get differentially dusty, which I think was one of the difficulties with the DES photometric calibration system. Having flattened the flat sky, we can subtract it. Fortunately, I don't have to talk about that. And also, fortunately, Yusra is going to talk about that, so I'm going to move on. Having subtracted the sky, you can correct the flat field to give the object flux for flat UF nu SED. So this means that as the atmospheric properties change, we've dealt with the emission part of it. We have not dealt with the absorption. I'm going to come back to the absorption in a moment. Object SEDs change. They change as the absorption changes in the atmosphere. That comes in below 1% or so. And as Eli will show you, we're already achieving well below 1% in the systematics and photometry. The better we can do, I think, the better the science is. I don't know of any flaw on that particular one. Though the requirements have the stretch goal is, I think, 5 millimags. The desk tell us that we ought to be pushing for 1 millimag, but they don't pay the bills. But those are the scales that we should be thinking about. We're not thinking about 5% photometry any longer, in which case almost everything I've talked about today is utterly irrelevant. Okay, so we should be in good shape to calibrate the sky objects once we know their SED. And we don't need to know the SED all that well to do the sky, but for precision cosmology we do. So I'm just going to briefly go over the properties of the auxiliary telescope. So here's the auxiliary telescope. It's this little dome over here on a mountain that I refer to as Patrick's Pimple. It's also known as Calibration Hill. It's really pretty small. Here's the auxiliary telescope. Here's the spectrograph that's stuck on the side, the so-called lattice instrument. What we're trying to do is to monitor the atmospheric transmission. As you all know, there are about 5 components of atmospheric transmission, about 6 free parameters, because the aerosol is a 2 free parameter thing. If we can measure these transmission curves, we can correct the SEDs to be above the atmosphere, or more likely, and maybe I put that on the next slide, we can correct the SEDs to a standard atmosphere, say at AMAS 1.2 on a classic photometric night, and minimize the effects of all the color terms. I think Eli is going to come back to this again. So here's some data. We're using a slitless grating, in fact, a Ronchi ruling, which has all sorts of nice properties. We were also investigating using a holographic grating, which had different nice properties. This is 90 lines per millimeter. This was taken a couple of weeks ago before we couldn't go down to Chiel any longer. This is a bright star. There's no reason not to work with bright stars. This is 6th or 7th magnitude. And here's the extracted spectrum. And some of these are A-star spectra, but you'll see that we're measuring the water band, the oxygen bands, we're measuring the water bands, and such like. So this is very much a proof of principle. This was extracted by Jérémy Neveu and Merlin Fisher-Levine. We've taken enough data to be able to see how well we can standardize the atmosphere and study its properties as a function of altitude, azimuth, time. So for example, here's the data we took a couple of weeks ago, sort of standard things you would normally do on a photometric campaign to understand the photometricity of your standards, except M104 is not a standard, except we took spectra for all these things. So we're going to be able to study the absorption properties of the atmosphere as a function of our mass and time. So Eli will talk about that. We're going to be able to study things as time and azimuth. I've already said that. So that's the end of my talk. If there are any questions, I will just remind you, this is not just a picture of the oxtail, it's also a picture of a condor. So if you have nothing better to do, you can stare at this picture and try to find the condor. As one of my colleagues said, you need to know about the wings of the PSR. And at that point, I can take questions.
Thank you, Robert, for that deep dive into LSST instrument signature removal. We have 2 questions. Gary Bernstein asked a question on Slack. Gary, would you like to ask your question again and see if Robert can give you an answer? I'll just unmute you in a second.
Yeah, well, I asked an entire question on Slack, which is, do you plan to do a CTE correction, or is this guy bright enough that it doesn't matter, or what, and how would you do that?
Oh, yeah. I think we're probably going to have to do a CTE correction, but I'm not quite sure. I haven't looked at enough of the data. I mean, if it's just a fill trap and the decay times are short enough, then of course that's not a problem. And there's also some work we've been doing, mostly the Slack group, on problems in the parallel transfers. The answer is CTE is nothing like HST. I think the standard techniques for sort of sweeping packets through will be sufficient if it turns out that we have to do it. But I don't think we really know yet. There was a CTE term in that page of equations.
Thank you, Gary and Robert. We have another question from Richard again. Just a second, Richard. I will unmute you. Richard, feel free to go ahead.
Sure. Hi, Robert. Do you know how well the out-of-band transmission will be measured, or are we going to rely on bench testing?
Yeah, okay. So we're measuring the out-of-band transmission as part of the acceptance procedure. We're not doing it on the full chips. I think we're doing it in parallel light at a range of angles rather than with a synthetic f1.2 very fast beam. One of the things I didn't mention when I was talking about the CBP is that we will have a filter holder we can put into the system. So we can do a scan of the QE of the entire system, including the optics and the detectors, without the filters in the beam. And we can then put the filter into the beam and do another CBP scan. Now, so we can separate out the effect of the filter from the optics. Now, it's very slow if you think that everything is a function of all possible angles. But if you're willing to assume that the filters are spatially homogeneous, for example, then it's pretty straight, and that the leaks would show up for on-axis light. Well, it's not on-axis, but for one particular beam angle within the annulus, then that's a pretty fast thing to do if you can do it very high spectral resolution. If you think that each point in the filter is special and it has its own angular dependence and there are leaks with bandwidths of 0.5 nanometer, then you could do that using the CBP, but it's an incredibly expensive operation. So the answer is we will do it in the lab, at least Materion will, I think it's Materion will do it. We will do some scans, most of which will concentrate on getting the details of the in-band performance, and then we'll do some scans well away from the filters to check for leaks. And of course, if there's any evidence for leaks, we can go in and look after them. It's one of the main goals for using CBP.
Okay, thank you, Robert. Thank you, Richard, for that question. The next question is from Aaron. Aaron, you are unmuted. Go ahead.
Actually, I had a comment, which was just to follow up Gary's question about CTE. Yeah, inside the camera team, there's been a lot of study of this. We see very clear evidence for what looks like traps or pockets in the serial register, at the end of the serial register. So this is a deferred voltage or deferred charge effect, not a transfer dependent CTE. I'm pretty sure that that's going to need correction. Some of the amplifiers show substantial traps, which we've studied extensively. So there's continued work on this by a few different people in the camera project. My student Adam Snyder is going to, a good part of his thesis will be studying and devising a correction algorithm for these effects. So.
I mean, the nightmare, as Gary knows well, in things like Hubble Space Telescope imaging, is that there are so many traps, and you get the noise correlations wrong if you correct them, because there's noise that's added that you have to move that isn't correlated. There's noise that is correlated by the traps. I don't think we're going to have anything at that sort of level that it's going to leak through into the lensing analysis, but we will have to be careful. This is the condor, by the way. I told you it was a hard problem, but you're all good at image processing.
Okay, thank you, Aaron, for that follow-up comment. Jean, I will unmute you now. This is a bit slow. Sorry, Jean, for some reason the unmute button's deciding to not work.
I could invent Jean's question.
Okay, I don't know what's going on here.
Oh, maybe I needed to unmute myself.
Can you try? Ah.
I can hear him now.
Okay, great. Go ahead.
Good to see you. And nice talk. I just wanted to ask about the auxiliary telescope. How many bright stars do you get in one shot, do you think? And how many exposures do you get in a minute or an hour, or how frequently?
Yeah, okay. So it's an LSST chip. So they have their little ways, but they also read out in 2 seconds. So you can say, let me take a stack of 15 biases in half a minute. It's really quite nice. We expect to get 1 bright star per field, but we can work at 6th magnitude. So I think we could include 1 star per LSST field. So that's 2,000 standard stars. They don't have to be standard stars. They'd have to be stars that we've observed on a standardizable night. And one of the things that Eli and Dave Burke, I think, will try to convince us of is that there are really quite photometric nights at Stereo John, which you can characterize. So on those nights, we have to observe our stars. Obviously, the nicer the spectra, the better they go. In reality, maybe we won't get 2,000, maybe we'll have 200 stars around the field, around the sky, and just observe them all the time. Things read out really very fast. So the telescope slews reasonably efficiently. And if we mostly follow the Auxtel after the first night, well, the first quote, sorry, let me start again. If we mostly follow the big telescope around, once we've learned the properties of our standard stars, we essentially have a spectrophoto standard, at least a differential spectrophoto standard, in every LSST field or near it. So all the slews are pretty small. So I expect to be able to keep up without any serious problems. Does that answer the question, Jean?
Eugene appears to be muted again.
Yes, it does.
Okay.
Oh. Good, thank you.
Thanks a lot.
Okay, and we'll have one final question now from Conrad. Conrad, go ahead.
Hi, Robert. How are you? Can you hear me?
I can hear you, Conrad. Hi.
Hi. This campaign of using a laser to map out the ghosts and the ghoulies and all these things,
yeah,
that involves mapping the full pupil and the full focal plane, right? So it sounds like a gigantic number of
yes,
artificial star experiments.
That's correct.
So do you have an idea how big an undertaking this really is?
I went through the numbers, yes. If you want to make I'm not sure that we do need to map. It's not clear that we're going to map the ghouls and ghosts this way, or just make sure they're not present in the photometry. So building a complete ghost catalog is difficult. I did go through the numbers and what it would take to do a complete filter scan, putting a beam at all angles through every point on the filter. So with the CBP, it's around, I must be able to do this. It's a 20-centimeter telescope, so 5. I think it's about 250 pointings for the numbers. I may have got that wrong. Something like 250 pointings, and then you have to put the beam through it all. So that's for the focal plane question. And then,
but then you have to map the pupil as well.
Same number. I shouldn't do these in my head, but you're right. If you wanted to fully explore the ghosts and ghouls at all possible angles, then it's prohibitive. And I don't think you could do the ghouls that way anyway, because they're coming off things that you don't know about. You'd have to deliberately shine, off the filters, off the baffles and things like that. Mm. So it's more a matter of getting the direct light, building the starlight, but basically building the chromatic star flats using it, in which case you worry much less about getting all possible angles.
Okay, thanks.
Okay, thank you very much again, Robert, for that talk, and thank you very much for the very interesting follow-up questions. We will take a break now of 30 minutes.